Next homework assignment is due on Wednesday. Remember, the test is only through Chapter 8. That homework assignment's over Chapter 9, so at least in theory, that homework assignment wouldn't help you preparing for the test, and hence why it's not due until after the test. Today, we will be reviewing material that will be on the test. So that means there's no clicker questions, and there's no homework due from today. The homework on Wednesday is from last Monday. So getting started, I finally got the first exam finished graded yesterday. It's been a lot of time. And so I am, by the way, for people who haven't checked this, you can see your exam on Moodle. So the people at Southwestern, you can go to Moodle, click on the exam one, and it has a return file that is your scanned graded exam. And you'll see there a rubric with how I broke down the scores, and you'll see comments about why I took off points here and there and whatnot. My theory has always been that exams are a big learning tool. That is, a serious student should look back through the exam, see what they missed, try to understand why they missed, and so on. And so that's why I spend so much time grading. But it's really, some students didn't get their exams back until yesterday. That's almost 4 weeks. And it's really not fair to students to have all of that time spent without knowing what their grade is. And, let's say that you got 0 on the test. You're like, well, if I would have known that a long time ago, I would have, done things differently. So I'm going to be grading the next exam differently. That is, I'm going to try to not make any marks on the exam, no statements or anything on the exam, just, X's and circles, and then have a little expanded rubric for my grading. So I'll have, instead of something like this, that's, you get, say, 1 out of 2 points on the figure because you had a figure that was associated with the problem but wasn't complete or wasn't correct. And, let's say you got 3 out of 3 because you nailed the concept. 1 out of 2 because you had at least one of the equations that could be used to solve it, but not all of them. That's how I've been doing it previously. But instead, I'm going to have this, and I'll just have, so I took a sample problem from an exam from previous year. The first question was on Newton's second law. And so, for the figure, did you have a free body diagram? Yes. Was it correct? Yes. And then I'll mark it like that. And so that's how I'm going to go through the grading. So I'll have more detail on the rubric that you can see on, but there won't be comments on the test.
Hey, we can't see your slides over here.
You can't.
When we switch to it, it's just a black screen.
Let me check on that then. Thank you for letting me know.
Mm-hmm.
Try that again. I must have hit stop sharing when I meant to hit hide before. Can you see them now?
Yeah, we can see them now.
Actually, yeah, I saw it flash on the reflection in the screen in the back. So yeah. So there will be more information here on the rubric about things you missed. See the ones that I highlight here, the ones I put E/E, that's going to stand for extraneous /error, which is obviously too long to put there. Because if you can't give somebody credit for having every equation on the equation sheet for each problem, then saying, look, I nailed it. I got the equation that I used, but then they have a whole bunch of other equations that they put on there because they didn't actually know what the correct equation was. And so that's what that one is. So that's a negative. This one here is a negative if you have error in your equations or extra equations that were not necessary, indicating that you were just trying to throw equations at it without knowing which ones to pick. So that's how I'm going to be grading. So obviously you don't see the rubric beforehand, because if you could see the rubric beforehand, you would know how to get all the points for each problem except for doing the actual work. So I'm just going to be looking for, use Newton's second law. If it says that, I would check off second law on the concept. Any questions about this revised method of grading? Okay, then it seems clear. So let's get to reviewing material. So chapters 4 through 8, the first of those chapters, chapter 4, we had forces. And so, of course, you need to know that a force is anything that pushes or pulls. And you need to be able to identify forces. So forces that you should be intimately familiar with include gravity, and you should know the two forms. Now, of course, you'll have these equations. Notice I wrote those both as scalar equations without the vectors. Gravity is always attractive. The first one only applicable if you are on the surface of the earth. The second one applicable all locations. So you should be familiar with that. The force of a spring minus sign to indicate that if you stretch a spring, it pulls back. If you compress it, it pushes outward again. The normal force, no equation for the normal force, right? I was reviewing with the student, and we get to the normal force, and I don't have equations. Like, well, what's the equation for the normal force? There isn't one. The normal force is the force necessary to keep from going into a surface. So it's whatever is necessary up to the limit of breaking the surface. Force of friction, remember there are two equations for that. Force of static friction is less than or equal to mu static times force normal. Force of kinetic friction is equal to mu kinetic times force normal. Force of tension, once again, there's no equation specifically for the force of tension. And I put here the drag force and the Stokes law. It's another kind of drag force. What's important about those is that one is proportional to speed, one's proportional to speed squared. And you're not going to be asked to identify when is Stokes' law going to be applicable, when is the drag force. Just you might have a problem such as, nope, not on this. I have one in the bottom of one of these slides that deals with using, in that case, actually the drag force. So you should be aware of these forces, know what directions they are, know why we have things like a less than or equal for the force of static friction, but not for the force of kinetic friction. So be familiar with those forces. And know Newton's three laws. Going really quickly through them, the first law is an object in motion stays in motion unless a force acts on it. The second law just puts an equation to that. The net force on an object is equal to the mass of that object multiplied by the acceleration of that object. And the third law, for every action, there's an equal opposite reaction, which says if I put a force on this mass puts an equal force on me in the opposite direction. So I'm putting an upward force to hold it up. The mass is putting a downward force on me. You also need to be intimately familiar with the free body diagram. Any problem that's going to use Newton's second law will definitely need a free body diagram, because the purpose of the free body diagram is so we can look at it and apply Newton's second law to it. So you should have those two intimately intermingled. If you have going to use second law, you better have a free body diagram. Question, Mahala?
Drag and Stokes' law is
Yeah.
on the equation sheet. So should we know those?
No, what you need to know is simply that the force of, the wind resistance, if you will, it can either depend on the speed or the speed squared, depending on the speed. That's really all you need to know. And you'll see I have a sample problem that uses that, and I give you a form that's just a constant B. Notice you have 1/2 rho and CD and A, and you don't know what most of those are. So I just give you a constant B that encapsulates all of that into it. And so on that one, I just give you, here it is. Okay, so make sure you can draw a free body diagram. Free body diagram, in theory, the free body diagram is you put a point that is your object. So if your object is a person, that person is the point. If your object is a train and all the cars on the train, That's the point. And then you show all the forces acting on that. It does not matter if you put force of gravity up and pointing down or below and pointing away, as long as you have it acting on that point. Either one is sufficient. But you show all the forces acting on your object of interest so you can use Newton's second law. If you have more than one component direction, make sure that you break forces into components. But in order to break into components, the first thing you have to do is identify what your coordinate system is, which is 90% of the time vertical and horizontal, but a small portion of the time you're going to choose differently. And so make sure you always have it identified. Chapter 5 was solving problems. I think this is the first one I have a problem. Yeah, I have a problem on here. So solving problems with Newton's second law, this is just application of chapter 4. Make sure that you draw a diagram to illustrate the problem. Draw a free body diagram. And remember the last page I said, in theory, it's a dot. If you have something like my diagram here, I am more than happy to have you draw your forces on that diagram and consider that your free body diagram. Right? I don't say, no, it has to be on a point. Now, this one here is rather convoluted. We'll get to it. So you have to identify your object of interest and your coordinate system, break forces into components. That's a break. Somehow the B. I didn't have, when I first wrote this, I didn't have identify the coordinate system, and so I added it. And apparently I deleted the capital B, which I now wrote as a capital, and forgot to put the B back in. Break forces into components, apply Newton's second law of motion in each direction. That's how you do force problem almost always. And then solve. Now, there was a problem I did recently where I didn't break it into components. I was just ready to break it into components, and I realized, hey, that was the equilibrium problem where the sum of the forces was 0, and I only had 3 forces. With 3 forces, it forms a triangle. And instead of breaking into components, I was like, I can do triangle math quicker than I can break into components. And so I used my trig functions, sine, cosine, tangent, law of sines, law of cosines would be the things available, but only if it's a triangle. If you only have 2 forces, sum of the forces, mass times acceleration, again, forms a triangle, and you can do that. That's why we had the problem on the first exam with adding vectors. You had to add them graphically because when we're doing these force problems, we're going to add our forces graphically if we're going to use the trigonometric methods to solve a force problem. Okay, so let's look at our first problem of the day. What is the acceleration of the blocks if there is no friction? So I've drawn a diagram. If I give you something like this, I will probably say you don't need to make a new diagram, but you need to make appropriate modifications. What would the appropriate modifications be for this diagram in your opinion, Isaac?
Adding forces acting on the block, like mass 2 high gravity.
Okay. Adding forces on the blocks. There's one other thing. Caitlin. Caitlin MacArthur. Other than adding the forces, yeah. Okay, the other important thing is putting your coordinate system there. And this one here, I'm going to do a real tricky thing with the coordinate systems. It's tricky because I'm going to make X and Y like this. Why did I make it so X is going up the slope? Because the acceleration has to be parallel to the plane. It's not going to go accelerating away from the plane and, it's not shooting off, right? So the acceleration is parallel to the X direction. And over here, I'm going to use a coordinate system that's supposed to be straight down. Like this. You haven't seen me do that before. You might have seen it in a homework problem, but you haven't seen me do it. I have 2 different coordinate systems defined. Why? As my son would say, just why? the acceleration is in the positive x direction in both cases. Right? All that pulley is doing, if that's an ideal pulley, all it's doing is changing the direction. And so my object is going to be mass 1 and mass 2 and the massless string connecting them. Isn't it nice to have massless strings that don't stretch? As soon as we make those, physics will become more real. Obviously, higher level physics, it is real, but here we make approximations. So my object is going to be those masses together. And when I make my forces and break them into components, a force in the x direction on mass 1 is not the same direction as a force in the x direction on mass 2. But they will be in the same direction in terms of the motion. So that was the other thing, the forces and the coordinate system. So now let's put the forces on here. Choosing black for the forces, apparently. So I'm going to, it's harder than people at Southwest because I don't know anyone's names. Starting with the gentleman in the black shirt and the black hat with an equation on the shirt. Yeah. Just name a force and direction that's acting on mass 1.
Normal force.
Okay, and what direction?
It's perpendicular to the surface it's on, so it's in the positive y direction.
That's right.
That's right.
Positive y direction. And what was your name? Just because I don't know anyone's names there.
Kenny.
It's what? Kenny. Okay.
If I mean the list is Kenneth Fallen.
Yeah. Okay. And next to him, what's a force that you see, Batman? Yeah. Did you say?
On mass 1?
Yes. I haven't heard an answer. If you answered, I didn't hear it.
Just gravity.
Okay, force of gravity. And that points, of course, down.
Yeah.
Okay, now, I said there's no friction, so we don't have friction to worry about. There is another force that is acting on mass 1. That force is the tension force. But that's an internal force to my system because my system is mass 1 and 2. So the tension force is internal, so I'm not going to show it because your free body diagram needs to only show external forces. So going, oh man, I should remember his name, to the next guy. Oh, no reprieve because she wasn't here when I was asking the question. Was it Thomas? Is that right? Yeah. So going to mass 2, what do you see acting on mass 2?
Gravity.
Gravity. And that's, of course, as with all gravities on the surface of the Earth, acting down. That is all the forces that we have. Okay, you can turn off the mic now. That's all the forces that we have to deal with on this system of two masses. As I said, there are two forces due to tension, but they're internal. And so now I'm going to apply Newton's second law. But before I apply Newton's second, I need to break things into components. So I'm actually going to, running out of space. Yes, zoom. Zoom so I can write smaller. So I'm going to have in the x direction and the y direction, force gravity 1, force normal, and force gravity 2. So let's stick with force gravity 2 because it's in my frame. That's already resolved into components. It's parallel to my x direction for mass 2, and hence that's just going to be so that was not hard. Now force gravity 1 and force normal, for those I have to look at this picture, and we see that force normal is parallel to y. That's what we were told by Kenny. And so I just put here 0 in the x direction plus force normal in the y direction. Notice I have a vector sign on the left, the force normal vector equals, and then I have a scalar force normal magnitude in the y direction. So there is a difference between those two force normals. One's a vector, one's the scalar, one's the magnitude. Finally, gravity, I need to break that into components. So there's M1G. To break into components, I always do dashed lines because that's how I keep things straight. I put a dashed line starting at one side of the vector that's parallel to one of my coordinate directions. So I'll just start at the top and go parallel to y. So that's parallel to the y-axis. And then go to the other end of the vector and draw a dashed line parallel to the other coordinate. And so this, if you start at the tail and end at the tip, the two components are going to have to add. So there's component 1, there's component 2, and the two components in red add up to my total that's blue. And then I have to determine where's the angle I know. Well, I gave in this problem a 37.5 degree angle between vertical and the incline. So I gave you the angle right there. So I need to find how that angle plays into my triangle. This angle here looks to be also between vertical and the incline, doesn't it? So if you were to actually, it's that there. And so that's the angle theta in this case. So now I can break into components. Which side of my triangle is in the x direction? Is it going to be the adjacent side to the angle or the opposite side from the angle? Adjacent. So adjacent cosine of theta is equal to adjacent over hypotenuse. Therefore, the adjacent side is equal to hypotenuse times cosine of the angle. And so my force, gravity 1 in the x direction, has a magnitude Now I have to determine if that's a positive or a negative. Looking at my arrow, is that parallel to x or anti-parallel to x? Anti-parallel, so that means it's a negative. So I've got the minus there. Now let's get the sign for the y component as well. Is that parallel? Is the opposite side parallel or anti-parallel to the y direction? Anti, so that's going to be minus as well. And to get the opposite side, it's going to be sine of theta. So there I've broken everything into components. Now to answer the question, I only need to look in the direction that's actually accelerating. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. What is my mass here? Okay, I have somebody that gave me the number. It's another person that gave me the equation. My object is mass 1 and mass 2, so the mass has to be mass 1 plus mass 2, which was the 150 grams that you said. So I'm just going to put in, adding from my columns, m2g minus m1g cosine theta equals m1 plus, okay, let's erase that line, m2 ax. And so to find the acceleration, I just have to divide both sides by m1 plus m2. And voila, I can now put in numbers and actually solve this. So I'm going to have my acceleration is equal to g multiplied by 50.0 grams minus 100 grams times cosine 37.5 degrees, all over 150 grams. Notice, depending on the angle, that could be a positive outcome or a negative outcome. So you actually have to get out the calculator and put in 100 times cosine of 37.5 degrees. I think that 37.5 degrees has cosine is 0.8. And so that would actually be on top 50 minus 80. So it'd be a negative 30 over 150 times g. Is that right? I went by memory on the angle being 37.5 degrees for a 3, 4, 5 triangle.
I get negative 0.26.
Negative 0.26.
I got negative 1.9.
Which probably matches my 30 over 150 times g. Yes, 29 point something. So there is an example of solving a force problem. Now, I didn't write down my concepts because when I'm solving the problem, I'm speaking a lot. But if you're doing it on the test, you're going to have writing your concepts. So what concepts did I use here? Okay, I used Newton's second law. And I actually, in my mind, there's one other piece that I used. Nah. The other thing that I used is break into components. Because I had to do that. So those are what, if you just put those two things, that would have been enough for this problem. Because it shows you know what you're doing. Right? It depends on the problem, how much explanation. But I'm not looking for super long things, but I'm looking for a clarity. There are a lot of people who had long explanations that I didn't see as actually explaining things. So when you look at my grading, hopefully you can understand what I'm looking for. Okay, let's move forward. Chapter 6 was circular motion and elasticity. Circular motion, what do you need to know about circular motion? Well, you need to know the variables. Now in chapter 9, we came back to circular motion and we started working with the kinematic equations in circular motion. So here we're not working with the kinematic equations. You need to know what the variables are. That is angle theta, how to determine if it's a positive angle or negative angle. We just use the right-hand rule. Now that we've learned the right-hand rule, if the angle goes like this, I take my right hand, wrap my fingers in the direction of that arrow about the origin. My thumb points out, and I say, aha, that's positive because my thumb pointed out. Or if you're using actual XYZ coordinates, it would be whatever direction you have assigned to the direction coming out of the screen. So, you should know angle, angular velocity, and angular acceleration, and understand why, and this is very simple. Why does something traveling at a constant speed in a circle have an acceleration? A lot of times people think acceleration means something changing the speed. It's going at constant speed, it's not changing the speed, but it's changing the direction. And acceleration is changing velocity over changing time, so that change in direction is an acceleration. And so we have the centripetal acceleration is the tangential speed squared divided by the radius, or the angular velocity squared multiplied by the radius. Those are exactly the same outcome because omega is the tangential speed divided by radius. So if you substitute that in, you find the two are exactly the same. So if something's going in a circle, we can calculate the acceleration necessary. Now, one thing that plagues students is centripetal force. Most students are happy with, okay, the teacher says there's no such thing as centrifugal, that inertia wants, things have a natural tendency to go straight and you have to have a force to deviate, and that's the centripetal force to make it go in a circle. But then when they draw a free body diagram, they'll draw a centripetal force. So they'll have, okay, here's a car going around a curve, so it's right here. It must have a centripetal force like this. And so in their free body diagram, they'll have the centripetal force and they'll have the force of friction in the horizontal direction. And that's wrong. It's wrong because centripetal force is not a force unto itself. It's not one of the things that we had here on our lists of forces. Centripetal force is a resultant. Centripetal force means the net force caused by whatever is actually applying forces. So you never, ever, ever, ever have that on your free body diagram because it's not a force acting on the object. Centripetal force is the sum of the forces. So you do sum of the forces toward the center is equal to mass times acceleration toward the center. This is the definition of centripetal force. It's the sum of the forces toward the center. Everybody understand why that doesn't appear in the free body diagram? Okay, because it's an easy mistake to make. Jordan.
Can you draw the free body diagram that way?
The free body diagram, the horizontal direction, that is if you're looking down, is what I have with that crossed off. There are two vertical forces, force gravity down, force normal up. But in the horizontal plane, it's just the one I have there. And so when you do sum of the forces, you just have force friction equals mass times acceleration centripetal if it's a flat problem like this. Right, that would be simple. Okay, so we had two fictitious forces here, the centrifugal force and the Coriolis force. Centrifugal force is fictitious because there's not something really pulling stuff out when you're going in a circle. It's just inertia. It has a tendency to go straight. If you were in a rotating system, like if you are on a merry-go-round and you say, I'm stationary, this is stationary, and the world outside is rotating around me, we can consider that a valid reference frame. In that reference frame, Newton's first law doesn't apply. And so we call it a non-inertial reference frame. And in a non-inertial reference frame, that's where you have centrifugal force can be considered real. But since we're learning physics in inertial reference frames, right? We learn Newton's laws only apply in inertial reference frames, then centrifugal force is fictitious. Then the Coriolis force, once again, it's a fictitious force. There's not really a force that makes a cannonball deviate when you launch a cannonball from your ship. It is just the difference in the speed of the surface of the Earth moving as it rotates. So that compared to the Earth, which we treat like it's an inertial reference frame, but really it's not, right? We're really rotating. And it's because of the motion of our reference frame that they appear to have a force making them deviate, because any acceleration, according to Newton's second law, would be because of a force. But understood correctly, it's not a deviation. It just looks that way, hence fictitious. Okay, a final thing in chapter 6, got very low coverage here, was the relationship between stress and strain. So we talked about the three types of stress. There's tensile stress, stress and tension, compressive stress, obviously in compression, and shear stress, which is when a force is parallel to the surface. So if I have my hand like this and I put a force that's pushing my finger that way, that would be a shear stress. So we have those three different types of stress, all of them having stress. The symbol for stress is a sigma, is equal to the force applied divided by the area it's applied on. I think it was Mahala asked, well, what's the difference between stress and pressure? And the difference is that there is directionality with stress. In fact, there's multiple directionalities. It's a tensor. You have two directions that you deal with in stress. For a class of this level, we don't go into the tensor at all. And so for a class of this level, it's almost like you think of it as the same thing, except for you can have the three types, compressive, tensile, and shear. And then we had strain was the deformation caused by the stress. And the relationship between those two is just the, I think it's the strain is equal to Young's modulus times the stress. I'd have to go look at what Young's modulus is. No, stress has got to be Young's modulus times the strain. Anyway, you'll have the equation if it comes up. That was a minor thing. It could come up, but it's not something we spent a lot of time on. Do you have a question, Randy? Yeah, okay. Okay, chapter 7. We're actually on pretty good time, although I had a problem down here to do. Let's do this problem because I think problems, especially Newton's second law problems, this is another Newton's second law problem. I think they help students probably more than just talking about the topics. You can always read the slide later anyway. So a snow skier skis straight down a slope with an angle of inclination of 17.5 degrees. If the coefficients of static and kinetic friction between skis and snow are 0.13 and 0.035 respectively, what is the skier's acceleration at low speeds? I said at low speeds to give you a hint that we are going to ignore air resistance. Now, there were at least 2 people on the last test that said, well, because of air resistance, this will happen. But I'd given explicit instruction, assume negligible air resistance unless specified. So unless you're told to include air resistance, assume that the effective air resistance is going to be small. If a snow skier is going really slow, the effective air resistance is going to be small. If they go very fast at all, then it starts to become considerable. So what's the first step I need to do to solve this problem? Yes, I'm going to draw a diagram and then add my forces. So I'm going to have my slope and the problem told me that I had an angle of inclination, which means the angle from horizontal of 17.5 degrees. And I have my snow skier. Got the boards there. So I've got a diagram showing what's going on, and then I need to show my forces. Now, I will just go with them. We have the force of gravity that's down, the force normal that's normal to the surface, and now I'm going to have a force of friction because I have friction explicitly mentioned here. Right? We assume no friction unless it's specifically invoked. What direction is the friction going to be for this person skiing down the hill? Opposite the direction that the person is sliding. So the force of friction is going to be up the slope. First key question, is that static friction or kinetic friction? Okay, I had a little bit of both answer. The key to answering a question like that is always, is there slipping between the two surfaces? Is there slipping between the ski and the snow? And the wording said at low speeds, which means, yes, it's slipping. So if they're slipping, then it's kinetic. If it was not slipping, it would be the static. So now I'm going to break things into X and Y components, but if I'm going to break them into X and Y components, what else do I need to add? I need to have a coordinate system. And given this problem, what is the really correct choice, the one that's going to make this easier for coordinate system? Not a left-hand coordinate system. Thank you, Jordan. X is parallel to the slope. Y is normal to the slope. I chose that because the acceleration is going in the X direction. Now, some people might say, hey, you only have 3 forces. Why don't you make a triangle again? The reason I'm not going to make a triangle again is because I have 3 forces and I have an acceleration. So that's 4 things. Now, 2 of them are parallel, but I only do that when I only have 3. I don't want to have one side as force of friction minus mass times acceleration, right? And so I'm going to break them into components. So which one of these do I actually have to do work to break into components? Just gravity. So once again, I'm going to draw. There's my mg. I will put dashed lines parallel to the y-axis going from one side, dashed lines parallel to the x-axis going from the other. And now I look at my triangle, and I have to determine which angle do I know in this triangle. It's not the same answer as the last triangle. Each triangle you have to look at and evaluate. So in this case, the angle between horizontal and the incline is the same as the angle between vertical and normal to the incline. Perpendicular and perpendicular. So there's my angle theta. Just as before, I have to have my components add to give me my total vector. And so the x component, just as before, is anti-parallel. The y component, just before, is anti-parallel. So they're both negative. But now the x component is the opposite side, which means I'm going to use sine. And for the y component, adjacent side, so cosine. Now, just to make sure it was clear to everybody, the trigonometric functions, sine and cosine, are in the opposite positions from the last problem I did because the angle theta was defined differently. You have to look at what angle you know to determine what trigonometric sign you're going to use to break things into components. Okay, then force normal is all in the plus y direction, so 0 in the x direction, force normal in the y direction. Force of friction is all in the plus x direction. We determined it was kinetic friction, so mu sub kinetic times force normal. There I've broken things into the components. Why do we break them into components? Why do we do a free body diagram? So we can apply Newton's second law. Now in this case, I'm going to put circles around my unknown variables. I don't know the force normal, and I don't know acceleration. So those are the two. I have two unknowns. If I have two unknowns, how many linear independent equations do I need to solve for those two unknowns? 2. So I'm going to have to make 2 equations to solve for that. I know acceleration in the y direction is 0. Acceleration in the y direction is 0 because I chose my coordinate system, so acceleration in the y direction would be 0. So I'm going to do some forces in the y direction is MAY equals 0 first. If I add those together, it gives me right away force normal equals mg cosine theta. Once again, a subtle note, force normal did not turn out to be mg, because people oftentimes just jump to that because a lot of the time it is. But you have to look at your problem. Now I do the other direction. Sum of the forces in the x direction is MAX. Add up my columns. Mu k times force normal minus mg sine theta equals MAX. Substitute in for force normal. Go away. Now I can cancel out the m's, and I have an equation that says the acceleration is mu k, well, it's g times parentheses mu k cosine theta minus sine theta. Notice the mass of the skier didn't even matter here. I didn't give the mass of the skier in the problem. I just said a snow skier. And in the end, we found that the acceleration did not depend on the mass if there's no wind resistance. If there's wind resistance, the one with more mass is going to have the wind resistance is a smaller proportion of the force of gravity, and so the more massive person will actually be closer to reaching this ideal if there's air resistance. The less massive person will have a lower acceleration. Hopefully solving these problems helps you. I know I really should have put a problem on this page that had centripetal acceleration because that's what we were talking about, but I didn't. Okay, chapters 7 and 8, the last two. Chapter 7, work, energy, and power. Now, I do have a problem on here that has to do with power. That's the one with air resistance. I'm going to go to chapter 8 and then come back and do it if we have time. So there's only 5 minutes left. So make sure you understand what work is, what energy is, and what power is. Work is a force doing something to an object. So it's a force with distance parallel. So we have that equation. Work is equal to force dot delta x. Force times the motion parallel. Or to put that in simpler terms, force times the distance times cosine of the angle between the force vector and the distance it travels vector. Energy is the ability to do work. It can be either because it's moving, kinetic energy, or because of configuration, potential energy. And power is the rate at which energy is converted, or the rate at which work is done. So power is work over time. Or if you use, I'll just use the second equation, the work is force delta x cosine theta over delta t, but delta x over delta t is the speed, v. So power is force times speed times cosine theta, if you will. Be able to identify conservative and non-conservative forces. Conservative forces, for our purposes, that's a spring force or gravitational force. Also electromagnetic force, as we saw in lab, but we aren't dealing with that yet. So for our purposes, it's just those two, the spring and gravity. Anything else that we're going to work with is going to take away energy or potentially add energy, so it's non-conservative. Be able to calculate with a graph, that is the area under the graph of force versus distances work. Know that energy relation and how to solve problems, which is on the next slide. And this last one, be able to evaluate when work energy is an easier solution, which is usually the case, or when Newton's second law is the easier solution. Why is work energy usually easier? Because if you have motion, right, you can't use work energy if there's no motion involved. If you have motion and the motion is changing directions, work energy doesn't care that it's changing directions. Whereas Newton's second law, that's a big deal. And so if there's change in directions, the work energy is pretty much always the easier one. If it's not changing directions, it could go either way. So how do we solve work energy problems? First, draw a diagram, right? Every problem, unless it doesn't say draw a diagram, draw one. Identify the energy at each important point. The work energy relation is comparing the starting and ending points. And so you just find the kinetic energy at the starting point, the potential energy at the starting point, kinetic energy at the ending point, potential energy at the ending point. Then if there is a non-conservative force, you need to calculate the work done by the non-conservative force in going from the start to the end point. Apply this work energy relation. The work non-conservative is change in kinetic energy plus change in potential energy. And then solve. So I guess it was on the previous slide where I had the problem. Yeah. The last chapter was on collisions. So make sure you know what linear momentum is, how to calculate it, when it's conserved. Remember Newton's second law, change in momentum is equal to the net force multiplied by change in time. So in our problems, we always had net force is zero. That was the key. Hey, if the net force on my system is zero, then my momentum is going to be conserved. Make sure you know the difference in elastic versus completely inelastic. We didn't work on anything in between except for as specified. So if you have a collision, it just says they collide and it's inelastic, assume that means they stuck together. Unless it tells you something otherwise, assume that means it's stuck together. Elastic means they bounced off and kinetic energy was the same after as it was before. And be able to solve one-dimensional problems and understand the rocket problem. I guess I don't have time to do this problem, but this is the problem with the drag force. And I said to calculate the power at speeds. What is power? I'm not going to draw a picture here because of time. We're done. What's the equation for power? Power is work over time, or force times speed times cosine of the angle between them. So for the car driving, the air resistance is going to be going the opposite direction of the speed. So the power is going to just be negative force times speed for the car. That's the power that's being taken up by the air resistance. So the power the engine needs is the positive of that. So I just take my force, BV squared, times my speed. So I'm just going to put the absolute value of the power. So the power is BV cubed. So if I triple the speed, that's going to be 3 cubed, 9 times more power necessary. And the energy necessary to go from point A to point B, if I triple the speed, takes 1/3 the time. And so I'd have 1/3 times 9 is 3. Oh, wait. That was 3 cubed. 3 squared is 9. That was my mistake. 3 cubed is 27. It's 27 times more power. And then for 1/3 the time, it would be 27 divided by 3, which is the 9, the energy. So going at a faster speed in your car does require more energy. Now, there are other things going on in a car, so it's not going to be exactly on that scale, like the fuel used versus the power you're using. But make sure you can do these kind of problems. We will have the test Tuesday right here at lab time.
I think we're